6.1, the standard normal distribution. A standard normal distribution has the following three properties. We know the graph is bell-shaped, and the mean is 0, and the standard deviation is 1. These two are going to be very important. You need those in order for it to be a standard normal distribution. We'll see others that are not standard, but for standard, we definitely need those two things. Mean is 0, standard deviation of 1. So we've got a continuous random variable with a distribution that's a graph that is symmetric and bell-shaped. We can say that's a normal distribution. We've got a bell curve, and we've seen this curve before. And you may remember these percentages like 34.1 and 13.6. That's the distribution of the numbers. We've seen before that this was the mean and 1 standard deviation away and 2 standard deviations away. That's kind of how a normal curve works. Remember, if it's standardized, then the mean is going to be 0. So we just kind of make it fit. We can actually draw a picture of this. We can graph this using this equation. It's kind of complicated, and we're not really going to need to graph it. I think it's kind of cool that we can though. So I actually graphed one in Desmos. You can see the mean right here is 10, and the standard deviation right here is 2.5558. But we type in that equation, it gives us this nice normal curve. We know it's not standard because we can see the mean right here is 10 and not 0. Uniform distribution is the other one. A uniform distribution is different. It's very similar. We're going to have area under the curve is going to be equal to 1, but that's all of our distributions. It doesn't have to be uniform. It's either standard or normal or uniform. The area under the curve is 1. So they talk about there's a correspondence between area and probability. A lot of the times when we're talking about area, we're talking about probability. When we're talking about distributions, they're kind of interchangeable. The area under the curve is also going to talk about the probability of whatever the problem is. So when we're talking about a uniform distribution, the values are spread evenly over the range, and so the graph makes a rectangular shape. All right, a rectangular shape. So if I drew out the density curve, it's not actually a curve. All right, it's going to be, every single value is going to be the same, so it's going to form a rectangle. All right, that's going to be a uniform distribution, a rectangle, different than normal. But we know the area of a rectangle is height times width. And so when we're talking about the area of the curve, it's just the area of that rectangle. And so remember, area equals length times width. It's the same thing. That's how you're going to find the area under a uniform distribution. All right. Now keep in mind, that's not the same thing as the normal distribution. The normal distribution is this curve. The uniform distribution is this rectangle. So our density curve is just whatever this graph is, whether it's a rectangle or a bell shape. And we know the area is exactly 1. We're going to use that a lot. Because the total area under the curve is equal to 1, there's a correspondence between area and probability. So there's that again. When we talk about area under the curve, we're talking about probability. Example 1, waiting times for airport security. During certain time periods at JFK International Airport, waiting times for passengers arriving at the security checkpoint are uniformly distributed between 0 minutes and 5 minutes, as illustrated in the figure. Okay, so this is a rectangle. This is a uniform distribution, not normal. Are all waiting times equally likely? Well, here are your waiting times, 0, 1, 2, 3, 4, 5, and all the waiting times are the same. So yes, they are the same. We can say all px, or the probability of any x, equals 0.2. Is it possible to have a waiting time of 1.2, 3, 4, 5, 6, 7 minutes? And again, that's yes, because this is continuous. Continuous, remember, means you can trace it from left to right. That is continuous. So it is possible to have 1.234567. It's right there. It's still going to have a probability of 0.2. So yes, all times between 0 and 5 are possible. Part C, find the probability that a randomly selected passenger has a waiting time of at least 2 minutes. I kind of like writing it like this. We want to know the probability that x is greater than or equal to. So if we look at the picture, the uniform distribution, we want all of these waiting times between 2 and 5. Well, between 2 and 5 is a distance or a length of 3, right? 5 minus 2 is 3. And so what we're talking about here is we want to find the area of this box between 2 and 5. And so area, we know area of a box is length times width. We're going to have 3 times the width. Well, the width is just this number right here, 0.2. This is going to be 3 times 0.2, which is 0.6. Probability that randomly selected passenger has a waiting time of at least 2 minutes is 0.6. That was easy with a uniform distribution. Now let's look at the standard normal distribution. Again, for a standard normal, you have to have this be true. We know it's going to be a bell-shaped graph, and the area is 1. But what's new maybe is we're talking about z-scores, okay? And when you talk about z-scores here down on the x-axis of this graph, z-scores are talking about standard deviations, okay? Specifically standard deviations away from a mean of 0. Things to know, we know z-scores refer to the number of standard deviations away from the mean. Positive z-scores refer to numbers greater than the mean. Negative z-scores are less than the mean. A z-score of 0 equals the mean. So make sure you know those things and understand those things. We've got this table, and this table is a little bit confusing, but this table is very, very useful for our standard normal probabilities. It's got z-scores along the left side and the top, and then all of these numbers inside the table are areas, okay? Areas and these areas are cumulative from the left. All right, so let's see how this works. If I said we have a z-score of negative 3.21. Okay, how this works is you find your z-score of negative 3.21. Now that's a little bit tricky because here's negative 3.2, but what you have to do is say negative 3.2 and 0.01 is negative 3.21. And so that corresponds with this number. This is an area. And so if you think about how your normal distribution curve works, you've got a mean of 0. And if you go over to the left, negative 3.2 standard deviations, what we are finding here in this table is the area under the curve to the left. Okay, areas are cumulative from the left. So we just found the area of that little bitty piece is 0.0007. That's what my z table tells me. So we've got all these negative numbers, and we've got a completely different chart for the positive numbers. But you need to understand that this chart is giving the areas cumulative from the left. So the table is designed only for a standard normal distribution. You can't use this for a regular normal distribution. You can't use this for a uniform. It's just for the standard normal distribution. There's 2 parts, one for negative, one for positive. And then it kind of tells you again, a z-score of 0.47 corresponds to a value of 0.6808. This is an area. or probability if you want to think of it that way, 68% or so. So how I read this on the graph, the mean in the middle is 0, and your z-score of 0.47 means 0.47 standard deviations greater than that mean. And then what we've just found is the area of the place under the curve to the left is 0.6808. This is how you can do it on a calculator. If you've got a TI, you press second vars to get to the distributions menu, and you select normal CDF. All right, notice we do not want normal PDF. That'll do something else. We want CDF for cumulative. We're going to input a lower score, an upper score, 0 for the mean, and 1 for the standard deviation. You're going to have 4 arguments. So let's look at an example or 3 and see how it works. Okay. So if I was doing between two numbers, like between negative 1.1 and 0.2, I would go into my distributions menu. So second vars, I want normal CDF, and I'm going to type in the lower bound of negative 1.1 and an upper bound of 0.2, and mean is 0 and standard deviation is 1, and paste that in. And that gives me a percentage, 0.4436. 0.4436. But what I just found was, I think it's very useful to look at the picture. You've got a normal curve. What makes it standard is this mean of 0 and a standard deviation of 1. So we're talking about the, let's see, where are we at? If we're negative 1.1 to positive 0.2, we just found the area of that region between those two numbers. The area is 0.4436, or the probability is 0.4436. All right, now, if we want to do z less than 1.54, this is exactly the same as how the table works. Okay, the table is aligned for this. So if I was using the table, I would find 1.54 in my table. Here I've got a different version, so let's look at this. 1.54. All right, so here's 1.5, find 04, match it up. Looks like it should be 0.9382. Okay, 0.9382. I can see it's going to be 0.9382 is my answer. I can see that from the table. But how you use that on a calculator is kind of weird. Consider your normal curve again, standard. We want to be less than 1.54. So 1.54 standard deviations is right here, and we want all of this area to the left of that. Now what's weird is, I think, this doesn't stop. It goes on forever to negative infinity. And so if you're using this, this equation, the normal CDF function on your calculator, you don't really have any way of typing in negative infinity. So the best thing you can do is just type in something that's way, way far over there. So negative 9999, or just something really, really, really far to the left, is going to approximate your infinity. All right, so I'm going to do the same thing with my calculator. I go into that second vars, normal CDF, oops, not normal PDF, normal CDF, and this negative 1E99, that's something that's really, really negative. So that's the same thing as negative 9999, 1.54, paste it in, 0.9382. Okay, so this does exactly the same thing as the table. If I want to be greater than a number, then really the only difference this time on my calculator is where those 9s go. This time you've got your mean of 0, and we want to be greater than negative 2.12. So we're talking about this. This is not how the table works. The table is going to give you this area right there. That's the opposite of what I want. Okay, so if we use that formula, if we type in the lower bound, the big number is going to be, way over here is going to be basically infinity. You just got to type in some big number, 0 and 1. and you're going to get, what is it, 0.983. All right. Notice, if we look at the table, negative 2.12, negative 2.1, oops, negative 2.12 is this right here, and that's not my answer. 0.017 is not my answer, but of course it's not, because it's giving me the wrong point. What was it? 0.017. It's giving me this region over here. You know, if I was going to use the table, I'd have to say 1 minus the region that I don't want is going to give me the region that I do want. All right. So it's going to be good for you to be able to use the table and also to use your technology. I've also, if you if you don't have a TI and still want to use some technology, find on Gold Adder, find the two different functions I've got for normal probability distributions. Okay, the first one is what we just did, and the second one we haven't seen yet, but it gets you both ways. All right, so check those out if you don't have a TI. Number 2, bone density test. A bone mineral density test can be helpful in identifying the presence or chance of osteoporosis. The result of a bone density test is commonly measured as a Z-score. The population of Z-scores is normally distributed with a mean of 0 and standard deviation. They have to tell you that so you know it's a standard. So these tests meet the requirements of a standard. Yeah, they have to tell you that so you know that it's a standard normal distribution. Part A, a randomly selected adult undergoes a bone density test. Find the probability that this person has a bone density test score less than 1.27. So really all they're saying is this, okay? Less than, this is what you use the table for, 1.27. So if you go to the table, you find a Z-score of 1.27, 1.2, okay, watch this. If I go, all right, here's 1.2, 0, 1, 2, 3, 4, 5, 6, 7. It must be this one. 0.898. 0.898. Of course, you could use your calculator. It would be, whoops, not binom. It would be normal CDF, and we want less than, so you're going to have to go from basically negative infinity to 1.27, mean 0, standard deviation 1. Okay, that's going to give you the same thing. Number 3, this time we want to be above negative 1, so it's the same kind of deal. If you're using the table, okay, think about your picture. Here's your normal curve, here's 0. We want to be above negative 1, here's negative 1. We want to be over here. Remember, the table doesn't tell you that. The table is going to tell you over here. So if we look at our table, you got to find negative 1 on the table, negative 1.0, negative 1.0 right there at the top is 0.1587, 0.1587. So I know this area over here is 0.1587. If I'm using the table, I'm going to have to say 1 minus that. 0.8413. 84% of the numbers are to the right of that. Okay. And again, if you're going to use your calculator, you're going to say normal distribution. This is a normal CDF. And the left side is negative 1, and the right side is something really big. And 0 and 1. So that's your technology. Number 4. This time we want to be between two numbers. Okay. Between two numbers is kind of hard to do. If I was writing it, I might say like negative 2.5 is less than Z and less than negative 1. It's kind of hard to do using a table. If we look at our picture, we want to be in between -1 and -2.5. Okay, so we want to be in between here. So what we're going to have to do with our table, let me fix that, is we would find this first number, this big number is -1. When we find that value in the table, we're finding the area to the left of -1, and we just did that a minute ago. That was 0.1587, but we don't want all of that. Basically, what we would have to do is we would have to find this area and subtract it. So looking at the table, the number to the left of -2.5, that area is 0.0062. And so in order to answer this question, we would have to subtract those two numbers. 0.1587 minus the 0.0062 gives us 0.1525. Now, all that said, it's going to be a lot easier just to use your calculator here. We can use our normal CDF in between -2.5 and -1 and 0 and 1. And that's it. That's probably even easier than the other two because I don't have to worry about infinity or negative infinity or anything like that. But that's going to give you that same result, 0.1525. Finding z-scores from known areas. Basically, this just takes you backwards. It's the same exact thing. It just takes you backwards. And what they're going to do is they're going to give you an area, and you have to be able to come up with the z-score. So I know the area is 0.6808. I find that z-score is 0.47. We're just doing the same thing. We're going backwards. So if using your TI, you've got a different formula, okay? This time it's inverse normal. And so you type in the area, you type in the mean and the standard distribution. Those of you with newer calculators are going to enter in this left. Some of you that have older calculators, it's not going to have that. And so you would just enter in those three. But notice if we type in that area, we get a z-score of 0.47. Okay, so keep that in mind. Oh, by the way, those of you with this calculator, this is where you would use that inverse normal distribution. Okay, this just goes backwards. Give it the area, it'll give you the z-score, or the score. Actually, it's better than that. Number 5, bone density test, finding a test score. Find the bone density score corresponding to P95, the 95th percentile. That is, find the bone density score that separates the bottom 95% from the top 5%. Most people get confused by the 95th percentile, but just think about your picture. Here's the normal curve. Standardize it. We're talking about the 95th percentile, so all that means is 95% has been colored in. Okay, 95% has been colored in, and we want to know that z-score. All right, so if you're using the chart, you have to use the chart backwards. Okay, you want to find 0.95. You want to find 0.95 in the body of this chart. And so I'm looking not on the left side, but in the middle of the chart, and I find 0.95 will be right in between these two numbers. Okay, that's my area. So I look here and I look right here. That's right in between 0.4 and 0.5. So let's call that 0.45. That's going to be 1.645. Okay. On your calculator, though, that's where you use inverse normal. You use that inverse normal, and the area is 0.95. Mean, standard deviation, left. And that's going to give you 1.645. Now keep in mind, and this should be obvious, I guess, but think about if you wanted this side. If you wanted this side, you would type in right. Find the bone density test score that separates the bottom 2.5% and find the score that separates the top 2.5%. It's two different questions. The bottom 2.5% is talking about find this z-score so that this over here is colored in. 2.5% is colored in. So, you know, you could find that in the chart, 0.25. 0.25, that's going to be in your negatives. Find 0.25. 0.25. Sometimes it's kind of hard to find. That one's 0.025, so that's not it. That's too small. 0.25 is right there. Okay. That's negative 1.96. Negative 1.96. That's the z-score that separates that bottom 2.5%. If you were doing your calculator, that would be inverse normal. You got 0.025 as your area, 0 and 1, and left. So now we do the top 2.5%, and that means we're going over here. We want this z-score for the top. And since we know these graphs are symmetric, it's pretty easy to see that this is going to be 0.196. Symmetry. Go to your table, find, well, I guess if you use the table, you got to remember something special. The table only deals with the left side, so really what you'd have to do is find the left side. You'd have to find 0.975 in that table to get your value. If you're using your calculator though, inverse normal, you have 0.025 and 0 and 1 and right. Or if you were going to simulate what the table does, I suppose you could do inverse normal, 0.975, 0, 1, left. It's all about which part of the curve you're looking at. I think it's much more efficient to just do the right side if your calculator will handle that. Critical values. For the standard normal distribution, a critical value is a z-score on the borderline separating those z-scores that are significantly lower, significantly high. Notation, this thing right here, z alpha, is talking about the area to its right. That's going to be important. You probably need to highlight that somehow. So when it says find, in example 6, find the value of z 0.025, it's talking about that area to the right. Okay, the area to the right, 0.025. Well, we just did that. We literally just did that in the last example. It was up there, 1.96. It was 1.96. If you're using your calculator, just make sure you understand that's to the right. You can go inverse normal because I've got the area. 0 and 1, and talking about to the right, that's going to give you 1.96.